Welcome back to Calculus. In this video I want to do just an example of a somewhat simple optimization problem so we can kind of just get some more practice with the process. And I'll do several examples over the next few videos. We'll get more complicated and intricate, I would say, each time. So what are we going to do this time? Well, suppose an engineer wants to build a rectangular castle wall, and because they're building along a river, you don't want to waste stone building your wall, right? So the side with the river doesn't need a wall, so we only need 3 sides. So we're making a 3-sided wall, somehow still going to enclose a rectangle, and we want to enclose an area of 8 kilometers squared. So that part right there is very important. And, you know, that kind of makes sense, right? Because you want to enclose an area, and if your people or the food stores or the archers or whatever have to get stretched out in some direction, that's okay. It's really the amount of stuff that you need to enclose that you care about. Now we want to do this so that we minimize the amount of stone used, and that is actually just a code word for minimize the perimeter, right? Because the amount of stone, assuming that the castle wall is uniform height throughout, the amount of stone should be proportional to the perimeter. Okay, so let's remember how this optimization process works. First we need to name the variables. You can do this with a sentence, like let x and y be 2 numbers, or you can do it just by drawing a picture. And a lot of times when you're doing geometry, just drawing the picture is a good way to go. So I'm going to build my river here. Or I'm going to draw my river. I don't really build a river, I suppose. So I'm going to draw my river. And then the castle wall is going to look something like that. I don't know whether the sides are short or long compared to the middle part, but I know it's some kind of rectangle. And let's just call the sides x and y. And then if the left side is x, then the right side better also be x since this is a rectangle. Okay, so that's naming my variables. I don't really need to say let x and y be the lengths of the walls and x is the one that there's 2 of or anything. Just the picture is enough. It really is. Okay, so now I want to write down the objective function and the constraints. Well, the constraint is pretty easy. So let's start with that. I'm told that the wall must enclose 8 kilometers squared. So let's say that the area equals xy, of course, that's the area that we're enclosing, and that has to equal 8. And I guess I'm going to keep track of the units here, because why not? But usually the units will work out, and you can just put them in at the end, at least in math class. But sometimes it's nice to be careful. Okay, so we have a constraint, and what are we trying to optimize? Oops, the objective function. What function are we trying to optimize? Well, we're trying to minimize the perimeter, right? So let's say we call that P equals, and what's the perimeter? Well, it's just going to be 2x plus y. Okay, so check. All right, now we note, of course, that P depends on more than one variable. This is a very common setup in optimization stuff, and we don't know how to minimize 2 variable functions, so instead we need to use the constraint to eliminate one of the variables. Okay, we want P to only depend on x or only depend on y. You get to do this however you want. So I'm going to solve the constraint for one of the variables. And let's say I solve for, how about x? So x equals 8 km squared divided by y. And then we plug that in. So let's call this P of y. It's only going to depend on y now. And this is going to be 2 times, and instead of x, I can write 8 km squared over y plus y. Okay, so that of course is 16 square kilometers divided by y plus y. Oh, I guess I could have put in some extra constraints now that I'm thinking about it. We also know x has to be greater than 0 and y has to be greater than 0. So if you want to include those, we probably already knew that. I mean, x times y equals 8, so they're both positive or both negative, and we definitely don't want negative numbers, but, you know, doesn't hurt to put it in. Okay, so now we have our P of y, and it depends on only one variable, and now we need to optimize this. So we're going to find the critical point, set them equal to 0. You'll note that y equals 0 is not in the domain of this function, and that's okay, because y equals 0 isn't part of, it's not allowed via the constraints, and y equals 0 wouldn't make sense for a rectangle anyways. But let's just note that we only want the y's greater than 0, not equal to 0, so we don't actually care about the 0 in the denominator. Okay, so what are we going to do? So take the derivative. P p prime of y. So let's see, we've got 16 kilometers squared. That is a constant. And then we have y to the minus 1, so we're going to get minus 1, y to the minus 2. So that's the same as dividing by y squared. And then plus the derivative of y, which is 1. Okay, so we take the derivative, set it equal to 0. Now we have to solve this for y, right? Okay, so I'm going to take this minus term here, that is really a minus 16 in the numerator, and I'm going to add it to the other side. So I get 1 equals 16 over y squared. This is 16 square kilometers. Multiply the y to the other side. So I get y squared equals 16 kilometers squared. Square root both sides. Normally I would put a plus or minus when I take a square root, but because I know y is positive, I can ignore that part. But make sure you note that we are ignoring an important part there. And that tells me that y equals 4 kilometers. Note that the units work out. It was 16 kilometers squared, and when you square root something squared, you just get the thing, right? So it's just kilometers. So y equals 4 kilometers is my critical point. So now I could go ahead and find x, right? X is 8 over y, so x would be 2. Or I could do the right thing, and I could check that my critical point is actually what I want. I do not know. I am not done with this problem, not even close. Instead, what I need to do is I need to check that this critical point is actually giving me a minimum. Okay? So that is very important. You have to do it every time. What do we have? I guess we could do the first derivative test or the second derivative test here. I kind of like the second derivative test again because the second derivative is simple. So p double prime is going to be, well, remember I had that minus 16 and then I had y to the negative 2. So then I have negative 2 y to the negative 3. Or, in other words, 32 over y cubed. So p double prime of 4 is going to be 32 over 4 cubed. And I don't really care what number it is. I just care that it's positive. Okay, so that means that p has a minimum. The graph is concave up, like that. So p has a local minimum at y equals 4. But I'm not supposed to find a local minimum, right? I need to find a global minimum. How could I possibly do that? Well, I have a rule for that. There is only one critical point. One critical point. Oops. One critical point. So the useful theorem says that this local minimum is actually a global minimum. P has a global min at y equals 4. Now that I know I actually have a global minimum, then I can finish the problem. I can find x. I can decide, what was I supposed to find the dimensions, the x and y that minimize the perimeter, or was I supposed to actually find what the minimum perimeter is? So for that, it's best to look back at the wording of the original problem. And this says, what should the dimensions be? Okay, the dimensions are what are the length and width. So I need to find x and y. I don't need to compute the actual perimeter. Okay, so remember I had that x equals 8 over y. This was kilometers squared. Oh, sorry, y is 4 kilometers. I should be a little more precise about that. And that means that x is going to be 8 kilometers squared over 4 kilometers, which equals 2 kilometers. Okay, so then we can finish it off with a sentence. The wall should be 2 kilometers by 4 kilometers. Oops, that's not right. X there. 2 kilometers by 4 kilometers. That's it. We could say to minimize perimeter, I guess, if we want to be fancy, but that's about it. So I hope that I have impressed upon you enough the importance of checking every time. You really do need to. You can't just stop when you have a critical point. You're only halfway done. But anyway, we will see some more complicated examples in the coming videos, and I will see you then.